Hi everybody. So today we will continue our exploration of the van der Waals gas. I'll just remind you where we stopped. So we have the equation of van der Waals gas, P plus A n divided by v squared multiplied by v minus n b, where a and b's are some specific constant, equals to nk Boltzmann T. Okay, so this is van der Waals gas. Great. Now, we know that there is some sort of transition when we plot the PV diagram. And in this PV diagram, we know that for sufficiently low temperatures, there is an area where dP to dV, somewhere over here, dP to dV is larger than 0, and this means that this region describes situations which are unstable and therefore forbidden in terms of equilibrium states. Right? What we explained by tons of examples is there's this equation in van der Waals gas describes some sort of a phase transition, okay, where the system should go from volume at specific pressure, from volume at VA to some other volume VB. Okay. And all of this forbidden area actually describes a transition temperature or transition from one phase to another phase. Okay, so in general, there is phase A and there is phase B. And all of this, where our stability criteria is not satisfied, describes the transition from one phase to another phase. What do we know, or how we want to define this transition? So basically, what we want to show is at what P the transition occurs. What are the values of VA and VB? So you want to characterize the transition. We want to find what is this critical pressure and what are the different volumes for phase A and phase B. How we treat the system. So yes, inside the transition itself, something violent and abrupt happens that we cannot describe by terms of thermodynamics or equilibrium states. But we can use the following reasoning. We can say, let's assume, okay, that, well, we know this from our everyday life, that we can have a separation in one single system between two phases. Okay? So this is our phase A or B, and this is our phase, this is phase, I want it to be phase B, and this is I want to be phase A. Okay? I can call this vapor, and this is going to be liquid. So I'm assuming that exactly at this point, somewhere at this point, I can take the two phases of the matter and look on them together sitting in equilibrium. Okay. So I rise the temperature a little bit, or I'm changing my pressure a little bit, and all of the system will become vapor, or all of the system will become liquid. But exactly at this critical point, okay, I assume that the two phases can coexist. Okay, so this is a coexistence of two phases. Moreover, I assume that this coexistence of two phases is some sort of an equilibrium, and it's not happening over here. It's some point that connects the two phases from over here and over here. Now, if this equilibrium indeed exists, right, what can I say about the different parameters that define the system? Right? They are in equilibrium. So what do I know? I know that if you want to describe one system, so first of all, there is TB, there is PA, and there is mu A. Okay? Those are our intensive parameters that describe the system, generalized forces. The same goes for the liquid. We have
why TB, PA, and mu?
Because I'm thinking awkwardly today. PB and mu B. So we have TA, PA, and UA. Now, the assumption of equilibrium leads to what? Leads to that the stability criteria. TA equals to TB. PB, PA equals to PB. Mu A equals to mu B. Equilibrium. Remember, in equilibrium, there are no currents. Therefore, the generalized forces are equal all over the system. What are those generalized forces? The intensive parameters: temperature, pressure, chemical potential. Great. So where it leads us? It leads us already to some sort of an equation that it can use. Now, as I told you yesterday, we don't want to use energy. Why we don't want to use energy for this? Because those lines where I'm working, okay, those lines are isothermal lines. Isothermal. Which means that I picked a specific temperature, I plugged it inside my equation of state, okay, and out of those equation of state I obtained the connection between the pressure and volume. So I'm working with a specific temperature. Now, energy is not a function of temperature. Energy is a function of entropy, right? So the conjugated variables, entropy, temperature. Energy is a function of temperature. Sorry, energy is a function of entropy. So I need to work with something which is a function of temperature. What we know that's a function of temperature. This is the Helmholtz free energy. It is E minus Ts. Okay. This is the quantity, or this is the chemical potential that I'm working with. Now, what is dF? It is minus S dt minus PV plus mu dN. PdV? PdV, yes. Okay. Now, because I'm working on an isothermal line, so I picked a specific temperature, and the temperature is constant, so T equals constant, all over the line, not just on this specific point, but all over the line. I kick out this minus SDT term, and I'm left with dF equals minus PdV plus mu dN. Now, let's look on this coexistence, or phase A and phase B. We know that there is the same temperature, but we already don't care about the temperature. So we know that the pressure is exactly the same, and the chemical potential is exactly the same. So we can write down the following. dF equals to minus dPV plus d mu n. at the coexistent point, somewhere over here, right? We know that the chemical potential is not going to change when we go from one phase to another, and the pressure is also not going to be modified when we go from one phase to another, because I'm assuming that I'm working at equilibrium. I'm focusing on the equilibrium, exactly on the coexistence point between vapor and liquid. So what do we have? We have that dF plus PV equals to d of mu n. Right. So let's forget about the differentials, because I can say that F plus PV equals to mu n. There can be some additional constant. This constant I can always plug in inside the free energy, right? Because free energy as the regular energy is always defined up to some additive constant. I don't care about what this constant is, so I am setting it to 0. Yes? Okay, so from what line you want an additional explanation? From here? Okay, so I kicked out the T because I'm working on an isothermal. Now, I'm not just working on an isothermal, I'm saying I'm working at the point of coexistence. Okay? So, where I am transitioning from a point over here to some point over there. The transition, I assume that occurs in equilibrium, and in equilibrium I have that my chemical potential is kept constant and my pressure is kept constant. Therefore, I can push those constant lines, not everywhere, but just at the point of equilibrium. I can put them inside the differential because they are constant values. Okay? Any other questions? Yes.
Why I can't to bring the PV inside with the F? I understand this line, but not
here from there?
Yes. Why it's legal?
So if I have dA plus dB, it equals dA plus B. It's the law of the differentials. It's like, think about it as some sort of a, if I have ddt of f of t plus ddt of g of t. You agree with me that this is ddt of f plus g? Exactly the same for the differential. Okay? So we have f plus pv equals to mu n. Now, it's not everywhere. It's not everywhere. It's just the transition from phase A to phase B. Okay? So what we're having, first of all, let's write it down. So mu equals to F divided by N plus P multiplied by V divided by N. Now, those guys are, you're talking about a bunch of particles. Right? We have a gaseous system or we have a liquid. It doesn't matter. It's a huge number of particles. This N over here is extremely large. Now, when I'm talking about chemical potentials, or from this equation, I'm saying, well, actually what's important at this transition, okay, it's not just the global energy or not just the global volume, it's the free energy per particle and the volume per particle. Okay, so we'll write the small v as v divided by n, and we will write this as small f as large free energy divided by n. So the equation becomes not just equation for the whole system, but in some sense we are looking on the behavior of a single particle in this system, right? This is the connection. Again, just around this point of transition from phase A to phase B. Now, moreover, I can say the following thing. If I'm already looking at the 2 points of this transition, I can write down, so let's write it down with the mu and p. So we have F plus P mu equals to mu. Now, it is on the left hand side and on the right hand side of the transition. So I basically can say that F FA plus P nu A equals to FB plus P nu B. What exactly have I done? I said that FA plus P A nu A equals to mu A, and FB plus PB plus nu B equals to mu B. So PA equals to PB, we just call it P. Mu A equals to mu B. Now this equality allows me to write down this equation. Now what goes next? This is a connection between the free energies and the volumes and the pressures of single particles, right? Per particle, it's fine, for the transition itself. So this equation, it defines the transition. What it says the following. Let's play with it. Okay, so we have FA plus P nu A equals to FB plus P nu B. Okay. So you can write down that FA minus FB equals to minus V nu A minus nu B multiplied by P. Therefore, FA minus FB divided by mu A minus mu B equals to minus P. You can say to me, why should I care, right? Why should I care? But this holds for the phase transition. Right? This equation we derive only for the phase transition. So we have two F's, we divide it by two V's, and it equals to some specific minus P. But we have a general connection, right? We have a general connection between the free energy and the pressure. What is the general connection? It comes from here. See? dF equals minus S dt minus P dV. So generally we know that dF by dv equals to minus P. This is general. So we have two equations for our plot. This only for the transition. This is a general thing. Yes?
Why it's general? We use me and F after we enter into the differential.
Divide everything by n. Okay, so you're asking me the following thing. Let's add this explanation. We know that dF equals minus S dt minus P dV plus mu dn. Right? Now this is a big F and this is a big V. Okay? Let's multiply everything by 1 over n.
But it's still differential. We get rid from the differential when we enter the.
N is a constant. Let's multiply everything. So we set the system. The number of particles in the system is constant. Nobody is entering in and nobody gets out. Okay. So if I define everything, it's a closed system. Right? It's a closed system. We started this by saying let's take a closed system. So if I multiply everything by a constant n. Okay, first of all, forget about this guy, okay, because n is constant, and I multiply constant n, So if multiply everything by 1 over n, I have 1 over n df equals minus s dt minus p divided by n minus p dv divided by n. Because n is constant, I can get it inside the differential because differential is like a derivative. So I have df divided by n equals to minus s divided by n. I'm taking care only of the extensive variables. Okay, so my dt minus p dv divided by n. And f divided by n is small f, and v divided by n is small v. Therefore, I have df equals minus small s. I'll write small s. This is large s. This is small s dt minus p d mu. Therefore, minus p is the derivative of f with respect to mu. df d mu equals to minus p. Therefore, this guy is general. Now you can also think about it by using the following strategy. F is extensive, volume is extensive, so it's always the number of particles multiplied by some free volume of free energy per particle, and volume is the number of particles multiplied by volume per particle. And the n cancels out. Okay, so this is general.
Can I ask a question?
And this is particular for the transition. Yes?
How do you know that each particle carries the same amount of energy? You have capital S energy, but you're claiming that each particle has...
No. I'm not claiming what happens to each and specific particle. I'm saying what is F is some average number. Energy is some average energy, because energy is fluctuating, free energy is also fluctuating. All of this is the average volume per particle, and this is the average free volume. Okay? Because all our thermodynamic potentials are some average quantities. They do not assume that everything is fluctuating. So we sit in equilibrium, and in equilibrium there is some average description of everything. Okay? Yes?
אמרת שהמשוואה כאן היא עבור המעברי פאזה. איפה במערכת הפיתוח השתמשת בזה שזה כאילו מעבר פאזה?
No. So, okay, the question, I'm saying that this is just for the phase transition, and where in my derivation I used that this assumption of phase transition. Over here. Over here, and when I assume that mu is exactly the same. Okay? So I'm saying I have some phase transition, I have differences, but mu is staying constant. Okay. Any other questions?
כן, יש לי שאלה.
Yes.
הנגזרת של F לפי ה-new הזאת.
V קטן,
לא
כן.
אמורה לכלול גם את dt ל-du? mu?
dt to d mu?
כאילו לא אמורים להוסיף סימן כזה של t קבוע?
Over here?
כן.
Yes, it's fine, but we are always working with constant temperature. So the moment that we started, it was written on the board somewhere over here. We are working with constant temperature. Everything on the board from then to till here is for constant temperatures. This is why I omitted it.
Okay, so.
Alright, so look on those two conditions. This guy and that guy. Let's write down our free energy. Now, free energy, similar to the problems with pressure and volume connection, also have some specific problems. Okay, so what happens if we plot our F as a function of V, as a function of U, it will look something like this. Now, what we have over here, it's a hint of where to search for phase transitions. Okay? This is the hint. So on any point of this plot, this guy is satisfied because it's a general connection between the derivative of the free energy, volume, and pressure. So this equation is satisfied everywhere. this equation is satisfied only in the transition. Okay. So I'm looking for 2 points. Let me try and plot it a little bit better. I'm looking for 2 points such that exactly those 2 points, I can connect them by a straight line. Okay. And the straight line will coincide with the function, and the derivative, so this is going to be VB, right? This is V, or nu B. This is nu A. This is FA. This is FB. So I'm looking for 2 points such that I can connect those 2 points by a straight line. You see, the equation of this straight line is going to be what? The slope of this straight line. The differences, this is FB and this is FA. So the slope of this straight line, it is FA minus FB divided by nu A minus nu B. Okay, so this is the slope. This is fine. But also, the slope of the function itself, okay, is going to be exactly the same at this point and at that point. Okay? So this is the criteria for the phase transition. Okay? This criteria tells us the following thing. Plot the free energy. You can plot the free energy per particle, or you can plot the general free energy. It doesn't matter. Plot the free energy and find 2 points, okay, on this straight line such that the derivative at this point, it is df to d ni at ni equals to nu A. The derivative at this point is df to dv ni equals to nu A. Okay. And what we know is that Fa minus Fb equals to nu A minus nu B. It's going to be equal to the derivative, to the slope of the function over here. df to d nu equals to nu A. Or it's going to be on the left hand side going to be equals to df to d nu of nu equals to nu A. So basically we're looking for 2 points where the derivatives of the free energy with respect to the volume are exactly the same. So this is the equilibrium condition. Now you can say, makes sense. Why it makes sense? Because if we look on one single point, this equation is going to be satisfied. If you take FA and somehow and say, well, I'm looking on a specific point where FA equals to FB and or over here, the derivative at this specific point, okay, is satisfied when VA goes to nu B. Okay, so if you take nu A and take this limit and say it converges to nu B, this is exactly in the limit, okay, this guy, in the limit, it's exactly the derivative. So this equation always satisfied when you take VA and it goes towards nu B. Right? But, and this is the interesting point, is there are some specific points where these derivatives are exactly the same, but the volumes are different. And our equilibrium criteria tells us, well, the system is going to jump from this position towards that position. Right? Everything here in between is unstable. This is a forbidden region. unstable. Therefore, the system, what it's going to do, it's not going to say, well, I will also have some specific volume over here or some volume over there. You getting to this point, you changing the pressure a little bit, and abruptly the system is going to move from this point towards that point. Okay? And this is the criteria that we can use in order to find those critical points. Okay? Those volumes at phase transitions and the free energy at phase transitions. So this is nice. Not nice as maybe doing it in another way, but it only used the fact that there is a coexistence of two phases. A little bit to the right, a little bit to the left, we're going to see only one phase. But there's some specific point where the two phases coexist. How this point is defined, solve this equation, and you will find the volumes and the free energies. Now, questions? This is still not good enough. Why it's not good enough? Because there is a nicer way to present everything. So usually the students, and also there's this free energy, but somehow we're feeling, oh, I don't completely trust this free energy. Pressure, volume, I can understand. So can we make this definition of our phase transition, or the criteria to find the phase transition, somehow nicer? Okay? And there is a way. It's called Maxwell construction. Okay, so what I'm trying to do is to make these criteria of a phase transition look a little bit nicer and a little bit more applicable. Maxwell construction. This is the same Maxwell from electromagnetism. Now, let's go back to this equation. Okay. So, what we know is that Fa minus Fb equals to minus P multiplied by Va minus Vb. Alright. But what this guy equals to? So we're working with constant temperature. We are working with constant number of particles. So we know that dF equals to minus P dV. Always. Why? Because dN equals 0 and dt equals 0. We're moving along this isothermal line. Temperature is not changing. The system is closed. Particles can go from one phase to another, but the total number of particles kept constant. So we know that dF minus pdV is exactly the same. So let's take an integral of the left-hand side on the right-hand side.
The V or Ni?
Ni. Okay. But it looks the same. We're going from state B to state A. Okay. So this integral equals to that integral from Ni B to Ni A. But what this integral on the left-hand side of this equation is equals to? If we have just a differential, this is Fa minus Fb. Okay. So we got that Fa minus Fb equals to minus the integral from Vb to Va of P dV. Let's plug this into our equation, and we obtain a criteria identical to this guy, but where the free energy is not involved. Okay? So what we are having that minus Va Vb P dV equals to minus P Va or ni A, ni B. We can work with volumes or we can work with volumes per particle, it doesn't matter. Okay, so look on this equation, what it tells us. So this is the Maxwell construction. Let's plot the geometrical interpretation of this equation. You use this equation in order to find the phase transition. What it exactly means. So, first of all, we're already back in the PV world, right? We are not in the free energy and etc., etc., etc. We have pressure, we have volume, we have the van der Waals equation that connects pressure to volume. We don't need to search for the free energy. Okay? This is why this Maxwell construction is nice. It uses the idea of free energy, but it's much nicer. And when you plot it and you understand the geometrical interpretation, it actually becomes very easy. So we have P and we have B and we have this behavior, right, with this unstable region. Let's plot the left-hand side and let's plot the right-hand side. We can forget about the minuses, right? We can forget about the minuses. What the left-hand side tells us. So you start with some specific VA, mu B, and you end with some specific mu A, okay? And you calculate. Okay, the integral is the area below the curve. So you calculate this area over here. Great. What is the right-hand side? You pick P, some P over here. You plot a straight line. Okay, this is our P. And you calculate what is P VA minus VB. You calculate the area of the rectangle that is plotted over here. So the Maxwell construction tells us that there is equivalence of areas. Okay? So the prescription or the algorithm to find what we don't know. Remember, the original question was, there is some forbidden area and there should be a phase transition. Okay, there should be a phase transition. Where this phase transition occurs, we used coexistence of two phases, we used free energy, etc., 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 and we got to this condition. This condition tells us the only thing that you have to do, you don't know P, you don't know V nu B, you don't know nu A. Okay. So the only thing that you have to do is to calculate, let's pick some general, nu B, nu A, and P, and calculate the area below the curve. You know how to calculate the area because you know what is the function, P is a function of V, so you know how to calculate the area. So you do this for some general P and some general VB, nu B, and nu A. The next thing that you do, you take exactly the same P, the same nu B, the same nu A, and you say, well, instead of saying that I have this crazy function over here, I have a straight line. I have a straight line. And now I just need to calculate the area below the straight line and find such P, nu B, and nu A where the black area equals to the red area. Yes?
איך אנחנו יודעים שזה מצב יחיד?
Oh, so great question. How do we know that this is the only solution that we get? Well, there is even a better question. This condition is not good enough. How many variables we have? Unknowns. We don't know this guy. We don't know nu B, and we don't know nu A. How many equations I provided to you in order to solve this? One. I have just one equation with three unknowns. This is not enough. I will answer your question in a second. but this is still not enough. Yes, yes.
אני לא יכול להגיד שברמת העיקרון יש לי את הקו הכחול והקו האדום, ובעצם השטח בין האדום לכחול מלמעלה ומלמטה הם שווים.
It's not enough.
אז זה
So
מקרה אחיד.
no. This is an equation that involves three unknowns. You have one equation you can think about as in mechanics. You have a constraint, one single constraint, three unknowns. It's not enough to solve it. Never. You have three parameters. Yes.
Didn't we say that nu A, the pressure at nu A equals to the pressure at nu B?
Fine, but we used it already in this equation. We used it.
But these are the two equations for nu A and nu B.
Great.
And then we have an equation for P, which is this.
Yes, this is the answer. So the answer is, listen carefully, this is equation number 1. Equation number 2 is, wait a minute, we have P as a function of V, right? So we know that, let's use the van der Waals equation. We know that P plus, or P plus A V divided by N, right? Squared, multiplied. This is nu A. Look at this. This is V divided by N. So this is nu A squared multiplied by V minus what we had in this additional case over here. What stands over here?
Bn.
Bn, right? Equals to N K Boltzmann T. This is still V. Okay, we need to connect our V to nu A. So let's divide the left hand side and the right hand side by N. I divide this by N and I divide this guy by N. So I get another equation which is P plus A nu A squared multiplied by nu A minus B equals to K Boltzmann T. Right, so we have two equations. Right, we have this equivalence and we have a van der Waals connection. But we can say, well, if you have already this for nu A, you can write the same equation also for this point, nu B.
The pressure at nu A and nu B is exactly
The same. Right? Remember, we started with that a coexistence of two phases. And at the coexistence, the pressures are exactly the same. The volumes per particles don't have to be, but the pressures have to be. Okay, so the third equation is, we write it exactly as this one. It is P plus A nu B squared nu B minus B equals to K Boltzmann T. Okay, so now I'm coming back to your question. I have three unknowns. What are my unknowns? Unknowns. P, nu A, and nu B.
But you have also T.
T is constant, I said it.
Okay, it's a constant, but you don't know which one constant.
Give me one and I will solve this equation. Right? I started that I pick a constant. So you can say, well, maybe for some specific temperatures, I won't have this solution, which is fine. And I will answer to that. Okay? But the starting point is you give me temperature, okay, in order for this equation. You give me the number of particles if you wish, but you don't have to because I can work on the level of particle of volume per particle, okay, and free energy per particle, and I solve everything. So temperature is a parameter that somebody has to provide to me in order to solve the problem. It's not an unknown. But I will continue on this a little while. So now three equations, three unknowns. Well, maybe, yeah, there are some general solutions, okay, which will mean that I don't have one single phase transition. I can have several phase transitions, okay, which is fine. But every phase transition, at least this is what we call the first order phase transition, is going to be defined by this Maxwell construction. So Maxwell construction tells us, Okay, when you find nu B, nu A, you find P, Maxwell construction tells us the following thing. This is P, this is V. What the system is going to do is, well, you have a continuum behavior, and this is going to be phase B. And you have also another continuum behavior where you're going to have phase A. But you're also going to have nu B and nu A, and you're going to have some specific critical pressure that is connected to your temperature. And what's going to happen is that the moment that you hit this critical pressure over here, and you lower it a little bit, just a little bit, okay? You lower the pressure a little bit, you're not going to transition to some slightly different volume. What's going to happen is that your system will perform a jump to this other volume. The free volume, or the volume per particle, is going to perform a jump from some small volume to a larger volume. And this happens, as we've seen from experimental situations, it happens usually very fast and very abruptly. Okay? In some sense, it's an uncontrollable transition. We can be very close to this point, we can be very close to this point, we can be at coexistence, but the moment that we shift out of those coexistent point, the transition usually is going to be extremely fast and violent. Okay? Now we know, at least for this simple system of van der Waals, how to find this transition. Now, I was asked a nice question about temperatures. Okay, so yes, I can solve this for each and specific temperature. Okay? I can solve this for this van der Waals. Now, moreover, if I'll provide to you some other equation of state, you can replicate my steps. Okay? Because, well, all this equivalence of areas, this special condition, I haven't used that it's a van der Waals gas or not a van der Waals gas, right? I use general description. The additional two equations, equation number 2 and equation number 3, those additional equations, they are the ones that help me solve exactly what P is and what B, nu A and nu B. But the equivalence of areas, it's a very general statement. And you can replicate this statement for any other equation of state, right? You basically can use this and see if there is a phase transition or not. Because the other guys are very simple. This guy, equation number 1, is very important. Now, how it's related to temperatures? How all of this is related to temperatures. Now, by the way, if I'm plotting this the other way around, if I will plot V as a nu, or V as a function of P, okay, what will happen? It will go all of this to reach nu A, and then it will jump abruptly to nu B. Okay. You remember the original equation has had some undefined behavior. Right? Now, instead of this undefined behavior, what we know is that there is going to be a transition. Instead of going up, down, etc., etc. Now, let's assume that I solved it exactly, and it can be solved exactly, for any temperatures that you would like. Okay. Now, remember that the van der Waals equation is not always looks like this. Okay. For high enough temperatures, it is perfectly fine. Okay, so I will just remind you what we plot, what kind of plot we had yesterday on the board. All right, so if we plot P as a function of B for different temperatures, so if the temperature is high enough, the derivative is always negative. Right? dP to dV smaller than 0, and everything is fine. It's only when we're getting below some specific temperature, this knee starts to develop. Okay? And at low enough temperatures, so this is T1, this is T2, and T1 is larger than T2, and I can also have T3, and T2 is larger than T3. So I have to go to low enough temperatures in order to observe this unstable behavior. Okay. Therefore, I can say the following. This equivalence of areas will occur only for low enough temperatures. Okay? Because for high enough temperatures, everything is always stable. And when everything is always stable, you don't have those ups and downs in your function. You don't have equivalence of area. So this is going to be equivalence of you just shrink this area to a single point. When you shrink this area to a single point, nu b is going to be equals to nu a, and this statement is trivial. Right? It's only for very specific behaviors. Now, what it means is that I should have some critical temperature at which, or below which, I will see phase transitions. Okay? How do I find this critical temperature? So I can do the following thing. Questions? I can do the following thing. I can start at very low temperatures. Okay? Let's use that. So let's say this is my temperature, and those are volumes, or knee. So I set up a temperature, T. Let's call it T something. And for this specific temperature, I solve everything, meaning I find the phase transition that exists at my system. And I assure you that, at least for the van der Waals, if you go deep enough or low enough in your temperatures, you will find this phase transition. So I went to very, very, very low temperature, and for this specific low temperature, I found a specific two volumes. Basically, it said to me, well, for this temperature, there's going to be a jump from nu b to this nu a. They are going to be dependent on this specific temperature that I chose. All right, I will increase my temperature a little bit. Okay, I will increase my temperature a little bit. Let's call it T I, and this is going to be Ti plus 1. I will increase my temperature a little bit, and I will see that, well, I will find another two different points where the transition or the jump from one volume to another volume occurs. I will increase my temperature a little bit more, Ti plus 2, and I will find another two volumes at which the jump occurs. Okay, so for each temperature, I find nu A and find nu B, and I plot those 2 points on the plot, and I do this for numerous temperatures. What I will obtain, you can do it on your spare time, what I will obtain is that it's going to be two solutions. For each temperature, two solutions. But the difference between those two solutions, the difference between the volumes, is going to shrink as I increase my temperature. Why it has to shrink? Because I know that if the temperature is high enough, there are no two volumes, there is no phase transition. So this function has to shrink. But what we are going to observe is something that looks like this. Okay? This is phase B. This is phase A. What is this? This is a forbidden region. Uncharted territory. Why it's forbidden? Because I know that if I'll try to get into this volume by changing my pressure a little bit, raise it up or crank it down, what I will see a transition from one volume to another. The system never stays in this area. Great. And I know that there should be also some very specific point that I call the critical point. PC. Critical temperature. So remember when I said, well, at the phase transition, I observe a jump, right? So there is a jump from one volume to another. But there is a specific critical temperature where there is no jump, right? Nothing happens over here. There is no jump for this specific critical temperature. What's going to happen? So what we will have is that there is a phase transition, but it has a name. It's a different phase transition. It's called a continuous phase transition. It occurs on only one specific temperature. It's not so rare, but it's delicate. Right? And this specific phase transition, it's continuous because there is no jump in the volume, there is no jump in specific heat, there is not going to be jump in entropy. I will explain you in a second. No jumps occurs for this phase transition, but it's actually very, very, very interesting. We will see it towards the end of the semester. So the usual first order, what we call phase transitions, are termed first order phase transitions. First order phase transitions. There is some specific jump in the volume, okay? And there is a acute points which we call second order phase transition. Which are much more delicate, nothing jumps over there, but from physical point of view, mathematical point of view, they are much more interesting. And when we will talk about Ginzburg-Landau theory, you will understand why. So if you're familiar with paramagnetic, ferromagnetic phase transition, this is the second order phase transition. So we'll come to this towards the last third of the semester. Great. So this is how you define first order, second order, how you define the different parameters for your phase transitions. Very, very nice. All of this was done for the specific example of van der Waals gas. It's a nice example, but we can generalize it a little bit more and have much more general statements. So a general statement about phase transition is this Maxwell construction, which does not apply only for the van der Waals gas, but there are some other criteria that you can say about phase transition. Specifically, I used here this first order and second order, but I haven't actually explained order of what. Right? So I want to be a little bit more specific about definition of a phase transition. Okay? And for this, I'm not going to use just the van der Waals example. You covered it, finished it, you know it by heart by now. I will I want to describe some general statements about phase transitions. And specifically, I want to describe this coexistence line, or coexistence of two phases. Yes?
שאלה על הגרף שעשית, מה בעצם קורה בטמפרטורות יותר גבוהות מעל הקו הכחול? הרי שם...
Okay.
לכאורה אמור להיות קו ישר כלפי מעלה.
The question is, what happens over here? There is just one phase. Just one phase.
עדיין יש...
Think about it from the following perspective. If you heat something really, really high, it's going to be in gaseous state, and that's it. No matter what you're going to heat, it's actually a good statement. No matter what you're going to heat, at some point the kinetic energy of all the different atoms, all the different molecules inside your system is going to be so high that interactions with the other particles, you don't care about them, and this is exactly ideal gas. So if you crank your temperature upwards, at some point you will hit this description of ideal gas, and there is no different phases for ideal gas. And this is what happens over here. You reach the behavior where dP, dV always smaller than 0. It looks like an ideal gas, and no matter what you have in your hands, if the only thing that is important is kinetic energy, interactions are not important, you're getting a gas, ideal gas. It's a trivial point up there, okay, up here, but it has to exist for anything. For me, for you, we're going to burn eventually, right? We will reach ideal gas. Yes?
אמרנו שהגרף של P כפונקציה של V משתנה עבור T מסוים. נכון? עבור כאילו איזשהו T קריטי. שאלה שלי אפשר לחלץ אותו מהמשוואה של ואן דר ואלס לצורך העניין.
Yes. So the question is, do I have to go through all this trouble in order to find this TC? And the answer is no, you don't have to plot this parabolic shape. You can go to this PV equation and search for what condition when you have first order derivative is 0 and the second order derivative is 0 as well. So you don't have a minimum and a maximum. You have a single point where the derivative is, I don't know the term in English. נקודת מעבר? No, there is another term. So it's not a maximum and it's not a minimum. So the first derivative is 0 and the second derivative is also 0. Okay, so you don't have a minimum and a maximum. You are going to take the second derivative. Yes? Saddle point. Yes. So, איך? נקודת פיתול, נכון. So we are going to have a saddle point. So you search for a saddle point, and this saddle point is exactly the transition when you have a minimum and a maximum. When you have a minimum and maximum, you have a forbidden region. So you somewhere over here. When you're above this saddle point, you're somewhere over there. And exactly for this critical temperature, those minima and maxima are going to coincide. Okay? And this is the critical temperature.
אני צריך לדרוש שתהיה רק נקודת קיצון אחת, רק נקודה אחת שמתאפס ושגם הנגזרת השנייה תתאפס.
Exactly. So you need to the following condition. There is only one point for which the first derivative of P with respect to V equals to 0, and exactly the same point, the second derivative also equals to 0.
And that's only for Van der Waals?
This is already a tricky question. So it's going to be already dependent on how exactly this P and V looks like. You will get an answer by the end of this class, not today, but of the semester when we talk about Landau-Ginzburg theory. There is an answer, but not for P and V diagram, for free energy. We'll talk about it. Other questions? All right. So I want to talk about this coexistence line. Right? What is this coexistence line? If I'm looking on, for example, not just P and V, but if I'm looking on P P and T. Okay. Not on the conjugated variables, but pressure and temperature. They are not conjugated variables. I know that there is going to be phase A and there is going to be phase B. And there are some specific pressures and some specific temperatures for which those two phases coexist. Okay? Now, the thing why we focus on this specific line is the following. From thermodynamical perspective, you use continuous functions to describe everything. So you describe all this phase and everything is continuous. You shift your parameters a little bit, the state shifts a little bit, everything is continuous. Your derivatives are continuous, everything is nice and beautiful. The same happens at phase B. Right? All the state functions, everything is continuous. But there are some transitions that are abrupt when you go from one phase to another. Okay, so your continuous description fails. It breaks down at some specific points or on some specific line. This is exactly the line when those two phases coexist. So I want to define this line a little bit more generally than just using this example of van der Waals. Now, for this we will need some additional statements from classical thermodynamics. Okay, so before going to this coexistence line, I want to show you something about some properties about energy, and I want to develop something which is called Gibbs-Duhem equation. Okay? So before going to phase transitions, some small deviation back to thermodynamics. Okay, so first of all, we're going to show that energy is a homogeneous function. So, as I said, thermodynamics, from a lot of perspectives, is a theory of continuum functions. Okay? It breaks at the transitions, but in general, it's a theory of continuum functions. So why I claim that energy is a homogeneous function? So we know that d equals to T ds minus P dv. Or in general, let's write it down, plus some generalized forces. You remember we used those terms. Dot generalized coordinates. Okay? Now, what will happen if I multiply my entropy or I increase the size of my system? I can say the following thing. So because entropy is an extensive quantity, I'm just saying, let's say that instead of S, I have lambda multiplied by S, where lambda is some positive constant. So I increase the size of my system. My extensive coordinates are also multiplied by exactly the same parameter, lambda. Okay. Now, I want to ask you what happens to the energy. So I had energy with specific S and X. And what's going to happen if I have an energy of lambda S and lambda X? Okay. So we're using this description of the differentials in order to answer this question. Okay. So I know that d equals to T d, I have lambda S now, plus F. Those are intensive quantities. If they are intensive, they don't care about the size of the system. So therefore, this multiplication by lambda does not affect not the temperature and not the generalized forces. Okay, so I have F multiplied d lambda X. Okay. This is actually very simple because lambda is a constant, I can take it out of the differential over here, and I can take it out of the differential for the right term. Okay. So what happens? I have lambda t ds plus lambda f dot dx. We'll continue this assignment, and I will have that this is lambda of t ds plus f dot dx. So let's write it down. This is d of e lambda s lambda x, and this is lambda multiplied by dE. So we're having d of e lambda s lambda x equals to lambda of d e of s and x. Basically it says that e of lambda s lambda x equal to lambda e of s and x. This means that E is a homogeneous function of first order. Maybe you had a class or assignments about homogeneous functions. In general, if I have omega of lambda x equals to lambda to the power n of omega of x, this is a homogeneous function, nth order. Okay. Why those homogeneous functions are interesting? Because Euler, very long time ago, proved a nice theorem about homogeneous functions. Okay, so Euler theorem for homogeneous function of first order. Now I will spare you the proof and will just give you the statement. If I have some general function of x1, x2 to xn, and I know that g of lambda x1, lambda x2, lambda xn equals to lambda of g x1, x2 to xn. So our theorem tells us that gx1, x2 to xn. All right. Equals to a sum I goes from 1 to n dg to dxi, where I kept all the xj's, all the other variables kept constant, multiplied by xi. Now, from this statement, I know something very general about my energy. If energy is a homogeneous function of first order, I can describe my energy in terms of the derivatives with respect to the extensive variables. Okay? So we apply this Euler theorem for homogeneous functions to energy. And we state the following. Since E of S and X is homogeneous of first order function of function of first order. Therefore, according to this Euler theorem, we know that E equals to dE to ds multiplied by s plus dE to dx I, or dx general, multiplied by x general. So E equals to ts plus f dot x. Okay. For example, E equals to ts minus pv plus mu n, and etc., 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 etc. It has to be satisfied always due to extensivity. All of this, specifically this guy, is the assumption that we started with for the first lecture. Energy is extensive. If it's not extensive, most of the stuff that we talked about is not applicable. We have to modify it somehow. The moment it's extensive, multiple options open in front of us. This is one of them. Now, why do I need this? I need this in order to develop something that is called Gibbs-Duhem equation.
Stas?
Yes.
In the equation E equals to Ts minus PV, where do we see that E is a function of S and V?
We forget about, we don't see it here, already here. You're right. We see it only from dE equals to TdS minus PdV. You don't know what the variables when you write it like this.
So can't we take this form of E and write it as a function of T and P?
No, because in order to write it down like this, you have to express T as a function of S and P as a function of V.
Alright.
Okay? Because your variables, the variables for which the energy is defined is S and V. Okay? All right, so let's start. So we have E equals to Ts minus PV plus mu n. Let's take the differential of this guy. So what is dE? It is d of Ts minus PV plus mu n. Okay. Let's do some very simple math. So this is d of Ts minus d of PV plus d of mu n. All right, so a differential of a multiplication of two functions is just as taking a derivative of a multiplicative formula. Okay, so we have s dt plus t ds minus p dv minus v dp plus n d mu plus mu dn. Great. Very nice. But now I can come back to your question and say, wait. This is all nice, all those homogeneous functions, but we know that d equals to tds minus pdv plus mu dn. So we have this equality. Okay. So we have s dt plus t ds minus p dv minus v dp plus n d mu plus mu d n equals to t ds minus p dv plus mu dn. We can cancel out a lot of stuff now. S dt, it's fine. TDS, TDS minus pdv minus pdv plus mu dn plus mu dn. And eventually we are getting to s dt minus v dp plus n d mu equals to 0.
why we assume that the extensive variables are constant?
They're not constant.
Not extensive, the intensive. Like
We haven't assumed.
dv is
No. They canceled out. We know that this equation holds, right? This we started. This is the first law of thermodynamics,
Yeah,
right?
right.
This guy we developed using the Euler theorem. They have to be exactly the same. So if d equals to this and d equals to that, whatever is left have to be equal to 0. That's it. And this is Gibbs Duhem equation. Now, why Gibbs Duhem equation is important for us?
It relates the energy to the free energy to the Gibbs energy and all this stuff.
Yes, but in the question of phase transitions, we can write d mu equals to minus s divided by n dt plus v divided by n dp. Okay, so remember the phase diagram P and T and something, and phase A and phase B. Something that connects P and T, okay, together by the means of the chemical potential, okay, is this Gibbs Duhem equation. Now, moreover, because we divided everything by n, let's use this as capital S, and this is capital V. So we have small s, which is large S divided by n. This is entropy per particle. Okay. And we have μ, which is large V divided by n. This is volume per particle. And we can describe the chemical potential by entropy per particle, the average entropy per particle, and the average volume per particle. d mu equals to minus small s dt plus small v dp. Now, why it's important? Because T and P are intensive parameters, intensive variables. In my phase transition, what do I want to do? I don't want to stretch the system. I don't want to increase in size. I want to observe a phase transition when I keep the volume or everything constant about the system. I pressure it a little bit more, or I heat it up a little bit, and then a phase transition occurs. This connection between intensive variables is described again by this Gibbs Duhem equation. Questions? No questions. Okay, so where we are going from here? Mu, what happens to mu exactly at the critical phase transition, or the phase transition? So first of all, we see that mu is a manifold, so some structure, two-dimensional structure, as a function of T and P. So if I would like to plot it, I will have the t-axis, I will have the p-axis, and I will have the mu-axis. Now, the assumption of continuum behavior says that, well, there is some two-dimensional manifold that describes the behavior of mu as a function of T and P. And everything should be continuum. Everything is continuous. Mu is a continuous function of T and P. But this continuous assumption does not tell us that the derivatives should be not also continuous, right? So what we will observe that there are specific lines on this two-dimensional manifold where the behavior, the transition from each point to another is continuous as described by this equation. But sometimes we can observe specific lines like this line over here, where mu is continuous as a function of t, and as a function of p, mu is a continuous function. It has this differential everywhere. But the transition, the phase transition, will happen where the derivatives of mu will have a jump. Okay? So this line separates phase A and phase B. There is a separation line between those two phases. What happens exactly at those lines? Those two phases can be at equilibrium. And the chemical potential at equilibrium, at coexistence of two phases, is exactly the same for phase A and for phase B. But there should be some abrupt jump, some abrupt modification. Where it comes from, so mu is going to be continuous, but the derivatives of mu don't have to be continuous. Okay? So at phase transition, the derivatives of chemical potential don't have to be continuous. The derivatives of mu don't have to be continuous functions. What it means that there are some specific situations where we are going to see abrupt jump of the entropy or a drop jump of the volume per particle. So SA is going to jump to SB, and mu A is going to jump to mu B, as we've seen for the van der Waals gas. This is what happens at phase transition. This is a first order phase transition. Jump. So first order phase transition. The derivatives are discontinuous. The derivatives are discontinuous. Okay? So this is the first order of phase transition. What is second order phase transition? The derivatives are continuous. The first order derivatives are continuous. But the second order derivatives of the chemical potential with respect to the intensive variables are going to be discontinuous. The second order means second order derivatives are discontinuous. Something much more interesting happens for the second order phase transition. We'll see this, okay? But for the meantime, when I'm talking about first order, second order, what I mean is that there is a chemical potential. The chemical potential is a continuum function. It's defined everywhere. And it's exactly the same at phase A and phase B at phase transitions. What separates the two phases? The derivatives of the behavior of the chemical potential. There can be a jump to the first order derivatives, and we'll see this jump. There can be a jump out of second order derivatives, third order, fourth order, and we can define any order of phase transitions. What we usually see in nature huge number of first order phase conditions. You're familiar with this from the heating experiment or heating water, right? There are some very interesting second order phase conditions that we will talk about later. So what we were left with, it's a small part that's already too late, is how exactly I define this coexistence lines, which is called Clausius-Clapeyron equation. I will develop it next week, but maybe you will see it also in your TA will show it to you. And we almost done with thermodynamics. So next week we're starting with principle of statistical mechanics. See you later.
Thank you.
הבנתי כאילו איך הגענו לנקודה הזאת, אבל איך החלטנו שבסדר ב-first order phase, כאילו הנגזרת היא לא...
אני טוען שמיו חייב להיות רציף.
נכון.
כי זה שיווי משקל. ובשיווי משקל, מה שקורה בפאזה א' שווה למה שקורה בפאזה ב'.
אבל הפייס טרנזישן לא בהכרח בשיווי.
אז אני טוען, לא. אני מסתכל רק על מעברי פאזה בשיווי משקל.
לפני ואחרי.
בדיוק. עכשיו, אני מסתכל על זה ואומר, בסדר, המיו חייב להיות רציף, אבל שום דבר לא מגדיל את החוסר רציפות של הנגזרות שלו. ואני מגדיר את החוסר רציפות של הסדר של הנגזרת